with Rayman Sums, LRAM, MRAM, RRAM. We did leftmost, we did rightmost, and we did middle. And I just wanted to show you some other types of Rayman Sums that the university can do. That it's not tested on AP, but that doesn't mean that we shouldn't know it, right? So at the university, they sometimes will do lower Rayman Sum and upper Rayman Sum. And if you have an increasing function, the lower Rayman Sum will look like a left ram, like an LRAM, but it's not. A lower Rayman Sum means you pick the lowest point on the curve. So we're going to do it. You're going to see right now. So this is an excerpt from UH, and it says, compute the lower Rayman Sum, underline the word lower, because it's not left, it's lower. From the given function, and they give us an easy function, they give us a quadratic, x squared between -1 and 1. So here's x squared, I'm going to exaggerate it. X squared between -1 and 1, I'm exaggerating it. Symmetric about the y-axis. I'm going to say here's -1, and I'm going to say here's 1. And they told me my partitions. With respect to the partition, and they go -1 to -1/4. So if that's 1 right there, I'm going to say -1/4 is like, let's see, like right there. And then from 1/4 to 1/2, so half is like right here. And then 1/2 to 3/4, so 3/4 is like right there. And then 3/4 to 1. So I labeled all my partitions. Are we ready? We haven't done anything crazy. I'm just waiting for you guys to catch up. What's up? Partition means between something and something. Like this is how thick my first rectangle is going to be. That's the width of my first rectangle.
So it's not like what we did earlier.
Yeah, where they were all equal. These are not equal width. Are we okay? It says with respect to the partition, and they tell me where my partitions are at. So the width of the first rectangle is 3/4. The width of the second rectangle is 1/2 plus 1/4. What's that? Whatever that is. And then 1/4. Okay. 3/4. The width of the third rectangle is between 1/2 and 3/4, so that's 1/4. And then the final one is 1/4. Okay. So here we go. Between -1 and -1/4, we're doing lower Rayman Sum. So lower means pick the lowest point. I'm going to do it in blue. So between -1 and -1/4, on that curve, where's my lowest point? So I'll go to -1/4. There's my first rectangle. Are we still okay? On the curve.
And why did you start at -1/4?
Because they told me my partition is between -1, -1/4, 1/2, 3/4, 1. I'm going in order by the partition. You know what I mean?
I understand you're going by partition, but I don't understand why you started at -1/4.
Oh, because the -1/4, that's the lowest point on the curve between -1 and -1/4.
Oh,
It says lower, so I got the lowest. All right, so here we go. Here's where most people make the mistake. Between -1/4 and 1/2, so here's halfway over here. I'm not just looking at those coordinates. I'm looking at the curve. At what point do I have the lowest point on the curve between -1/4 and 1/2? At 0. So there's my second rectangle. This one technically doesn't have an area because they're right on the y-axis, on the x-axis. Does that make sense? We're doing lower Rayman Sum, so this is probably why it's not tested on the AP.
So instead of looking at the value,
The shape of the curve, the lowest point on the curve. Between 1/2 and 3/4, where do I have my lowest point? 1/2, so here is my third rectangle. And between 3/4 and 1, 3/4. So if I was just looking at the positive part of x squared, sorry guys, if I was just looking at the increasing part of x squared, it would be an LRAM. Like you can't tell the difference, but the difference is the partitions, right? They tell me how to partition it. All right, are we still okay?
yeah.
Okay, so now we're just going to calculate area of those rectangles. And how do I calculate area of a rectangle? length times width. So let's see. The width between -1 and -1/4, that is that 3/4? So 3/4, and now I'm going to find the height. The height is -1/4, and you square that dude. I guess technically you don't have to put the negative if you don't want to.
Why is it?
Because the function is x squared.
Okay. Oh, gotcha.
Plus, and if you want to be technical, what's a half plus 50? 75? 3/4? 3/4 times 0 squared. That's technically the second rectangle. Plus, the difference between a half and 3/4, that's 1/4. So 1/4 times 1/2 squared plus 1/4 times 3/4 squared. How do we feel? All right.
So it's 1/4 because that's the distance.
3/4 and 1.
Oh.
I'm just doing width times height, width times height, width times height. The width between 3/4 and 1 is 1/4. The width between half and 3/4 is also 1/4. Yes.
The 3/4 where it's multiplied by the 0 squared, where's that
From 1/4 negative all the way to 1/2. That's the width.
from? Oh, gotcha. The negative.
We still okay, guys? Let's see what that is. 3/4 times 1/16 plus 0 plus 1/4 times 1/4 plus 1/4. I'm trying to do it without a calculator as much as I can, like that. And then 16 times 4 is 1632. That's 64, I believe. 3/64 plus 0 plus 1/16 plus 1632, so 9/64. And the only one we got to change common denominator to is this one here. So 4/4. So we get, let's see, 3/64 plus 4/64 plus 9/64, which is 9, 13, 16. 16/64, which reduces to 16 goes into 64, is it 4 times? 1/4. How do we feel? Yeah.
So is the partition thing specific lower and upper sums, or will you see that with like LRAM?
No, it's specifically for like the university one for this. You'll probably, you might see it at your university. I haven't seen it on I have seen it on UT test, yeah. But obviously it's going to come out on UH if you go to UH. It's just something for you to know. You know, it's not going to be tested on the AP exam, but your professor will probably want you to know it.
If you have like if you have an LRAM, or sorry, if you have an MRAM regular midpoint, would you, and then they gave you
Partitions?
partitions?
They probably would not do partitions with MRAM. They probably would do partitions with lower or upper.
Not left and right?
Well, left and right is like, you know, common with leftmost point. Maybe they do partitions with left and right, but definitely they wouldn't do partitions with mid, because then there's going to be human error. Like, well, what's the middle? And especially if it's very, like, you know, there's a lot of little partitions. You still okay, guys? All right, let's keep going. Compute the lower Raymann sum. So another LRAM. I should have put an upper RAM. That's fine. With the given function, sine x over the interval 0 to pi, with respect to the partition, 0, power 6, 3 power 4, and pi. Okay, so let's do this sine curve. Let it take up most of your paper here. Try to make it symmetric. Bam, right there's pi over 2. And I guess that's pi over 4 and 3 pi over 4. I'm going to use blue for my partitions. I haven't done anything crazy yet. Are we still okay? Pi over 6. Is pi over 6 to the left of pi over 4 or to the right of pi over 4? To the left. Probably like right here. Doesn't have to be perfect. And then it wants lower. So between 0 and pi over 6, where do I have my lowest point? At 0. So technically, you don't have a rectangle there. Between pi over 6 and 3 pi over 4, where do you have your lowest point on that curve? At pi over 6. There's going to be just one rectangle. At 3 pi over 4, from 3 pi over 4 to pi, where do you have the lowest point on that curve? At pi. This is a really bad estimation, but they asked us to do this, so that's what we're going to do. You will probably not use lower Riemann sum to calculate the area of sine x, because you can see how bad this estimation is. But it's fine. That's so let's see what that area, let's see what that rectangle is. So the width is 3 pi over 4 minus pi over 6. We'll calculate that in a little bit. And the height, we're using pi over 6. What is sine of pi over 6? Do you guys remember? 1/2. So let's see. We're going to have to find a common denominator maybe? Yeah. So times, what's the common denominator? 12. So 3 times, this times 3 times over 3, and this times 2 over 2, like that. So I get 9 pi over 12 minus 2 pi over 12. And remember, we still got to multiply that by half. So 9 minus 2, that is 7 pi over 12 times half. So 7 pi over 24. Is that in there? Yes. Where did I get the what?
Not the 1/2 of the other part.
3 pi over 4 minus pi over 6. I got it from width of a rectangle. This is a 3 pi over 4, and this is a pi over 6. And if I subtract that, that'll give me.
The other one is just like on
I just did the difference of 3 pi over 4 and pi over 6 will give me the width of that rectangle. You know what I mean? Oh, sine of pi over 6 is a half. The y value up here from the unit circle, that has to be a half. That's my height. Yeah, that was it. What do you guys think? Nothing, right? It was like whatever. So it was a little weird, but keep that in mind. Yeah. Yes, the curve, the height of the curve is dictated by the equation y equals sine x. I can't even, y equals sine x. So, because I used pi over 6 to dictate my height, sine of pi over 6 equals a half. We got some more questions, guys? Okay. I can answer questions all day. It's all good. Keep hitting me. All right, here we go. Have you guys ever seen the sigma notation before? Yes. Some of you have, some of you haven't. They used a lot in statistics, for those of you that are going to take statistics next year. So I have some sum. This is called a series. Sequences in series, you can also call it a sequence. 1, 1/4, 1/9, 1/16, 1/25, 1/36. And you can see there's something going on that's very obvious. In the bottom, it looks like you're just squaring. 1 squared is 1, 2 squared is 4, 3 squared is 9. By bottom, I mean denominator. 4 squared is 16, 5 squared is 25, 6 squared is 36. And we have this notation here. So what this means, that j equals 1 is your start position. Notice where that it starts at j equals 1, and I have a j there. And that 6 is your stop position. and you're just adding each integer from 1 all the way to 6. Does that make sense? This is not the only way to do this. There's a whole unit on this for those of you that are going to Cal 2. There's a whole unit dedicated to this. It's called sequence and series. I don't remember. It's the very last unit. And all they do is this, a whole bunch of them. This is not the only way. There's another way to indicate the same sequence. You can do this. You can say sigma, and do you want to use a different letter besides J? It doesn't matter to me. C. C equals, let's start at 2. And if I start at 2, let's see, I'm going to have to end at 7. And I'm going to go 1 over C minus 1. Close it squared. Travis, that's not going to work. Yeah, it is. Look, start at 2. 1 over 2 minus 1 squared plus 1 over 3 minus 1 squared plus 1 over 4 minus 1 squared plus 1 over 5 minus 1 squared plus 1 over, am I going to be able to fit the last one? 6 minus 1 squared plus 1 over 7 minus 1 squared. Is it the same? 1 over 1 squared? Yeah, it's the same, guys. So there is an infinite amount of ways. See? Yeah. And trust me, they do. But not right now.
Yeah, it could be like 1 over cosine x.
What's up, Arispe? Ask. Oh, because they told me right here, can you think of other ways?
Oh, so you're just like.
I'm just making it up.
But like.
I'm sure there's others besides subtracting.
So if it was just like c squared, then would you just start with like 1 over c squared?
No, if I wanted to look like this one, I would start at 1. Because I want it to look like this sequence. 1 over 1, 1 over 4, 1 over 9. This one starts at 2. So you told me 1 over c squared. If I start at 2, I'm already starting right here at that one. 1 over 2 squared is 4. You know what I mean? Okay. Don't worry, we're not there. If you want to take the next sequence, it's Cal 2, and it has a whole bunch of that. All right, right now, we're not going to tie it up to the integral symbol, not yet. We're just going to practice with that summation. What is this Greek letter called again? Sigma. That's a sigma. S-I-G-M-A. All right, it says I, and it says I equals 1. Show me the sequence. What is it? What's the very first one? 1. Then I put a plus symbol. 2. Then I put a plus symbol. All the way until. There you go. I don't know what that is. Add them all up. Someone. It's 21? Okay. 6, 5, 11, 15. Okay, I trust you. Whatever you guys say. Cool? Let's go to the next one. It starts at 0, so let's go ahead and show all of those. So 0 plus 1 plus 1 plus 1 plus 2 plus 1 plus
3 plus 1.
Mm-hmm. Sorry, I was waiting for you guys to take over. And there it is. And then drop the parentheses. There's nothing in the front. Go ahead and add them up. I don't know what that number is. Is it 21 again? Oh, okay. I think when I wrote them, there's different ways to show 21, I guess. So maybe the last one's also 21 too. I don't know. I think it might be. Ready? We start at 3. 3 squared plus 4 squared plus, okay, we already know. It's not going to be 21. 6 squared plus 7 squared. Done. You stop at 7. I don't know what that summation is. It's some number. It's definitely not 21. It adds up to something. What it adds up to is not necessarily important. What is important is the concept that you know what it means. Because remember, eventually we're going to add an infinite amount of rectangles. So that's what we're leading up to. Like, oh, add rectangle 1, add rectangle 2. Notice on this one, there are 2 letters. 1 over n, k squared plus 1. And it starts at k equals 1 and ends at the n. So every single term is going to have a 1 over n, but the last one is going to be the one that you terminate. So usually when you have a sequence like this, because this one goes on forever, you're going to start like this. 1 over n, and then the k starts at 1. So 1 squared plus 1, close it, plus, usually show 3 of them immediately. 1 over n, 2 squared plus 1, close it, plus, again, 1 over n, 3 squared plus 1, close it. After you're done that, you go plus, because it would have been a plus, and you put 3 dots. Dot, dot, dot. The 3 dots insinuate that you continue with this pattern. And you're going to continue with this pattern until the very last one, which is the n one. Usually they go n minus 1 over n minus 1, like you show the last 2 terms, so I'll show you. Actually, you know what? We're not advanced yet. I should not show you. We're just going to go to the last one right off the bat. 1 over n, parenthesis, n squared plus 1, close it. And then put, for now, put, what should we put? We're novice? Novice. Did I spell novice correct? Novice, like we're rookies. The most correct way is you show the last 2 terms. So that's why we put novice in there. So if your professor looks at it like, oh, okay, you're a rookie right here. Let him slide. No, your professor will be fine. The most correct way, for those of you that are dying, I want to know the correct way. Don't write this down because we have to talk a lot about it. The most correct way would have been 1 over n minus 1, and then you show like the last digit, n minus 1, close it, squared, plus 1, plus, this is the second to the last term, plus, and then you show this one, which is the last term. Yeah, that's all it means. Okay, if you want to write it down, write it down. But that's what it means. But I just went ahead and just showed you the last one. Cool or not cool? If you open up a textbook, it'll probably have that like written that way. All right, ready for this one? Look at this. Is this looking similar already? So check this out, guys. F of x. Okay, I want to tie it up, but we're not going to tie it up 100%. Do you agree? When we were looking at, well, not this one, but when we were looking at yesterday's notes and we were finding rectangles, LRAM or whatever. Sorry, I'm making it sound like, okay, this was like the first rectangle, the second rectangle, and what we did was this was the delta x there, and then the height was determined by the height of the curve. Okay, so check it out. This is like your height. And this is your width. And you can already see it's starting to look like the notation that we're going to see in a little bit. That actually almost looks like an integral. Look at that. If you look at it carefully, it almost looks like an integral with a dx on it. A delta x turns into dx. I don't want to give too much away. All right, so here we go. We're going to start with the very first one. There's a subscript. It's a subscript in the bottom, so we're not squaring anything. It just means like the first one, the second one, the third one. So f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. Are we still okay? That x1, x2, x3 just literally means first one, second one, third one on some number line. You're not squaring or doing anything. It depends on the function. Plus dot, dot, dot. You guys want to do it the rookie way or the novice way or the right way?
The right way.
All right, the right way. Here we go. F of n minus 1, close it, delta x, plus f of n, close it, delta x. There it is, the right way. Second to the last one, and then the last one. Are we feeling okay? Nothing crazy, right? Don't worry, we'll have a full-blown lesson on Monday. Bring your A game on Monday, sleep well Sunday, because sometimes it's heavy, sometimes it's not. It just depends. If you have a clear image and you are well rested, you'll be fine. But if you're tired, it's going to be hard to take it all in. So get sleep on Sunday. All right, ready for this next one, guys? All right, it's the same concept, nothing crazy. They tell us a function here, and they tell us this. So first, let's evaluate this, and then we'll see what this function like adds up to. You know what I mean? So here we go. I'm going to go sigma from k equals 1 to 5 of f of k over 2 plus 3 equals, here's the first one, f of half plus 3, close it, plus f of, let's see, 2 over 2 plus 3. I know that's a 1, guys, but I want to show all the work. Plus f of 3 over 2 plus 3 plus f of 4 over 2 plus 3 plus f of 5 over 2 plus 3, close. We're going to find out what those are. So let's see. 1 half plus 3, isn't that 3.5? So we're going to figure out what that is. 2 over 2 plus 3, that's going to be 4, so f of 4. And then 3 over 2, that's 1.5 plus 3, so 3, 4.5. So it looks like it's going by half. And it is f of 5. And finally, 3, 4, 5, 5.5. You remember yesterday where we showed you how to do it really quick? Take your calculator. Yeah, remind me, seniors, to give you guys I want to give you guys a calculator. That way you can always use it and have it. I mean, I'm not giving it to you guys, just borrowing it for the remainder of the year because it's not mine to give, it's the school's, right? I guess this equation would have been easy enough to do it by hand, but we already started with the calculator, so too bad. Negative 2x plus 3, put it into y1. y1, negative 2x plus 3. And then I'm going to go, there it is on y1, negative 2x plus 3. And now I'm going to go to my home screen. And where did I start off at? Which one? 3.5. So start at 3.5 and go all the way to, is it 5.5 by 0.5? So alpha, trace, enter 1 at 3.5. Close, plus alpha, trace, enter at 4. Plus alpha, trace, enter 4.5. All the way to 5.5, right? Hopefully I didn't make any mistakes. I am getting negative 30. All right. So all that is nothing more than negative 30. Probably good notes if you could tell me what negative 3.5 is, what 4, 4.5, and then what is it? Negative 4, negative 5, negative 6, negative 7, negative 8. It makes sense. It's a linear line, and we're going by half. So yeah, it makes sense. And look, it's the same thing for this one. So I think you guys already got it. So see if you guys can be fast. You don't have to. Just see if you can. 3 times 1 is 3. 3 plus 3 is 6. 3 times 2, 6 plus 3 is 9. And you can already see the pattern. 3 times 3 is 9, 10, 11, 12. 3 times 4 is 12, 13, 14, 15. And I think this one's easy enough that you don't necessarily need a calculator. You can if you want to. F of 6 is 2. F of 9 is 4. F of 12, you want to take a guess, is 8. F of 15 is 11. And then add them all up. 11, 19, 23, 24, 25. 25. Say it again. Did I mess up? 9 minus 4. Oh, it's 5. So then that's going to mean that's 26. Yeah. Thank you, miss. I would have done it wrong. I think we're right. You okay, Rodriguez? Everyone's like, don't be sad that we're here, guys. Be happy. I actually wanted to come to school yesterday, guys. Not because I want to torture. Hear me out. Not everyone in the inner city has a warm place. You know what I mean? So I was like, the way I would have done it, I would have said like, come to school if you're cold and relax. We're not gonna torture you. You're just gonna be here, and if you want to work, you can, and if you don't, that's fine with me too. I would have not pressured anyone to do any work. I would have just been like, just you're here, you're warm, nice and warm. You know what I mean? Because not everyone has a warm place, guys. So, you know, thank our lucky stars that we're pretty healthy and fortunate. All right, so here we are. I think, what do you guys think? Pretty simple, pretty straightforward. How much time do we still got? Do you think we have enough time? No? All right, so during 7th period, make an attempt on your Delta Math. It's over this stuff that we did, and you should be able to finish it during 7th period. So yeah, that's it, guys.